Welcome back. This is class number 7 in our discussion of industrial electricity. We're going to start today by going over a roadmap. In this class, we have been exploring concepts of direct current. In the very near future, we're going to move to alternating current, and then we're going to move to motors. Today, you are right here. We are making the transition. So far, we've explored things like Ohm's law, power law, efficiency. We looked at things like the power flow diagram, where we talked about a power in, a power out, and a power lost. We mentioned series and parallel circuits. In our last class, we introduced the voltage divider and current divider. In this class, we're going to briefly introduce Kirchhoffs Current Law and Kirchhoffs Voltage Law. We'll refer to those as KCL and KVL. We're also going to take a short segue into battery capacity, and then we'll move into alternating current. We mentioned this before. Alternating current has a component of trigonometry. Magnetics is involved. We also have a few new components, including the inductor and the capacitor. I do have some good news for you. All of these things that we talked about in the world of direct current are also applicable to the world of the alternating current. Ohm's law is still with us. Power law is still there. Efficiency, these power flow diagrams. We can have series parallel AC circuits, voltage divider, current divider, and Kirchhoffs current and voltage laws. They all apply equally to AC and DC, except for the battery, because batteries are a DC device. To get us started with today's lecture, let's review the voltage and current divider. We said that the voltage of interest is equal to the resistor of interest over the total resistance multiplied by the source. We had to be specific here because this T, this total right here, is the series component. Right? The voltage divider is applicable to series circuits. Here's a for instance. If we had a 20-volt source and several resistors, so let this be 20 volts, let this one be 10, 5, and 7. If we were curious about the voltage on R2, so let this be R1, R2, and R3. So what we're looking for is this voltage right here. We can use the voltage divider. Here's how it works. The total series resistance in this case is 10 plus 5 plus 7, which gives us 22 ohms. We would say the voltage, behind my head, let's try that again. The voltage on R2, because that's the one of interest, is the resistance of R2 over the total series resistance multiplied by the source, which gives us a voltage of about 4.55 volts. Again, the voltage divider is very useful, and it's applicable to series circuits. The current divider is for parallel circuits. It tells us that the current of interest is equal to the total resistance of the parallel piece over the resistor of interest multiplied by the source. Again, be careful. This T right there is the parallel piece. Here's an example. Let's let this be 7 amps. We'll let an R1 be 2 ohms, an R2 be 4 ohms, and an R3 be 6 ohms. And this is an ideal current source. The total parallel resistance is 1 over 2 plus 1 over 4 plus 1 over 6. If you work that through your calculator, that's 2 inverse plus 4 inverse plus 6 inverse equals, and then you invert that result. So it's about 1.09 ohms. And now we use our current divider, and we say that the current through R1, I didn't specify that, did I? Let's find the current through R1. So the current through R1 is the total parallel piece, so 1.09, divided by the resistor of interest, which is 2, multiplied by the source current, which gives us a current of about 3.82 amps. So there we have it. We have the voltage divider, we have the current divider, the voltage divider. This T down here is for the series piece. In the current divider, that total is for the parallel piece. Okay. So again, that would be this piece right here. You'll often hear me refer to that as the resistance of the box. Now we can talk about Kirchhoffs Voltage Law. It tells us that the summation, this is the sigma symbol, of the voltages on a closed loop is equal to 0. So that's the summation, closed loop, and we're interested in the voltages, equals 0. So the summation of the voltages on a closed loop is equal to 0. Here's an example. We'll start with the battery, and we'll put a second battery here, and let's put another one here. A rather peculiar circuit, but that's all right. We'll see how it works together here. Let that be an R1, and this will be a 6-volt battery. And we can put the polarity marks in. That's not necessary because we know that the larger bar is the positive polarity for the battery. Here's how it works. We are going to start in the lower left-hand corner, and we are going to take a walk on this circuit. We are going to walk in a closed loop. So we're going to walk all the way around the circuit back to where we started again. Again, a closed loop. Along the way, we're going to add up the voltages, right, which is what this piece says. So the summation of the voltages on a closed loop should equal 0. That's what we'll do. Starting in the lower left-hand corner, we would write -2, because we walked in on the negative terminal of this battery, minus 8 plus the voltage on R1 plus 6 equals 0. If we solve for that, we would say the voltage in R1 is equal to 4 volts DC. And maybe you could have done that by inspection, because if you looked at this, you would have said, if I were to put a voltmeter here, this is 2 volts plus 8 volts, and the batteries are indeed connected up together, like so, negative to positive, so this would be 10 volts here. And if you were to put a voltmeter here, you would say, well, there's 6 volts, and if you put a voltmeter here, which is voltage R1, by the way, that voltmeter would read the difference between the 2 voltmeters. In this case, it would be 4 volts. Before I forget, there is a simple rule we need to follow, and that deals with the polarity of a source. So let's say we have 2 different batteries. So we've got this one and this one. You can see they're opposite polarities. if you were to walk, right, if you were to take a walk through this battery, you would say you're entering the negative terminal. So you might call that negative 2 volts. If you were to take a walk through this battery, you'll notice you're entering in on a positive terminal. So you might call that 6 volts. And that's what we see here. We walked in on the negative terminal. So that's where that 2 volts came from, right? That's where that negative came from. And here we walked in on the positive terminal. That's where the 6 volt came from. Again, if you walk in on a negative terminal, you get a negative voltage. If you walk in on a positive terminal, you get a positive voltage. Moving on to Kirchhoffs current law, we learn that the summation of the current going in is equal to the summation of the current going out. So the summation of the current flowing into a node is equal to the summation of the current leaving the node. As my old professor said, you got to make sure that the goes intos is equal to the goes outas, right? Goes intos is equal to the goes outas. Another way of saying Kirchhoffs current law is to say that the summation of the current in a circuit, the summation of a current at a node is equal to 0. Here's an example. Suppose you had a node, and that node had several currents that were flowing in and flowing out. Here we have 2 amps flowing in. We have 12 amps leaving. We have some unknown X, and then we have 8 amps leaving. So the goes intos got to equal the goes outas. So we write that here as a reminder. Current in is equal to the summation of the current out. Going in, we have 2 plus X. Right? That's going in right here. That's going in. Leaving the circuit, we have 12 and 8. If we were to solve for this, we would say that the current X is equal to 18 amps. So X is equal to 18 amps. Let's see if that makes sense. So going in, we have 12 and 8, so that's 20 amps going in. And then leaving the circuit, we have, let's see, we have what, 8 and 12, which is 20. Okay? And that statement is true for any node. Before we start our trigonometry, let's take a sidebar here and talk about battery capacity. For any battery, we know that the capacity is the product of current and time. We could shorten this up and just say the capacity is equal to amp hours. You may have seen this with battery packs such as this. So this particular one is a lithium-ion battery. It has a 350 milliamp hour rating, and it happens to be 3.7 volts by 2 batteries. And you can see that there are 2 cells in there. In this case, we would say the capacity is equal to 350 milliamp hours. Knowing that, we can play games with it. We could say, how long could this battery pack power an LED that consumed 20 milliamps? So we would say 350 milliamp hours is equal to, and what do we say, 30 milliamps? So 30 milliamps multiplied by time, which would be hours. So that would be 350 divided by 30. Okay. Make sure we have our units correct. So if we divide, we get rid of milliamps on both sides. So that leaves us with 11.6 hours is equal to the time. So this battery pack could power a 30 milliamp LED for about 11.6 hours. While we're here, I want to point something out. You may have seen cells that look like this. Right, so you have a positive terminal here and a negative terminal here. If you look close, you may be able to make out this number where it says 18650. So 18 tells you the diameter and 65 tells you the length. It tells you the diameter is 18 millimeters and the length is 65 millimeters. And this is a pretty common cell that you're going to find. And this particular one is a laptop battery that I took apart just to see what was inside. Okay, so again, 18 is the diameter, 65 is the length. There are also larger cells like the 2170. So that would be a 21 millimeter diameter and a 70 millimeter length. If you have some time, I'd encourage you to look on the internet and find these two cells. Find those two cells in association with the electric car and see how these battery packs are put together. I think you'll find it pretty interesting. That takes care of our sidebar of capacity of a battery. What we're going to do now is move on to trigonometry. Suppose we have some magnets. We have a north and we have a south. Between those magnets, there will be a magnetic field. Into that magnetic field, we place a rotor that has two wires on it. We'll put a dot here and we'll put an X here, which is going to indicate the current flowing into and out of the page. To help you visualize this, I'm going to draw what it looks like in 3 dimensions. Something like that, where you have a north magnet, a south magnet, and curved faces. There is a magnetic field between these two. And into that, we insert the wire. All right, so we have a coil of wire that's free to pivot about this point. Now we can talk about the current that's flowing in this loop. So we'll go back to our 2-dimensional world. Again, you can see now that we have the 2 magnets, we have the magnetic field, and then we have this member that is free to rotate. And this is what happens as we rotate, right? As these 2 wires move in the presence of a magnetic field, a sinusoid is induced on the wire. So a sine wave is produced. That sinusoid looks something like this as a function of time. As the loop rotates within the magnetic field, a voltage is induced on the wire, which causes a current to flow. The amplitude at any moment in time, for example, the peak amplitude is there and the negative peak amplitude is there. The amplitude at any point in time is dependent on the physical position of the coil. The minimum occurs when the coil is situated like so. So when the coil is in this position here and here, there is 0 voltage. If that position is moved and we end up here and here, which is here dot, and here, we are at a maximum. Now, you remember we talked about magnetic flux lines, and we talked about a wire moving through those lines? If we're in this position, you could say that that wire is cutting across the flux lines. It's cutting across the maximum number of flux lines, giving us the maximum voltage. However, in our original position, we were right here. And when you're here at the very top, right, we're talking about this position right here. When you're there, there is no flux lines being cut, so the voltage is 0. So again, in this direction, no cutting of flux lines. In this direction, we are cutting flux lines, giving us the maximum voltage. Okay, so we were at the 9 and 3 o'clock. So let's go and erase that. Of course, we'll leave this piece here. And now, if we are in this position, right, if we're in this position, we find that's another minimum because we're moving this way. We are not cutting flux lines. Let's put that over here. So that would be X there, like so. Okay, so that's a 0. We end up at a minimum when the rotor is in this position. And then finally, we're back to where we started, and the rotor has gone full circle, and we're in this position right here. So again, as the rotor turns, it will sweep out a sinusoid, and the amplitude of that sinusoid is completely dependent on the physical position of the rotor. From trigonometry, this is very much related to the unit circle. We will call this the real axis, and we're going to call this the imaginary axis. And we're going to let our line segment, so let this be our vector, and it is going to rotate in a counterclockwise direction. And I think you will agree that no matter where this vector is, right, no matter where it's pointing, right, as we change the angle, it's always going to be the same length. From the unit circle, we can describe the position of this rotation using two terms. We could talk about the imaginary piece, and we could talk about the real piece. Or we could talk about this angle theta. Okay, these are all different ways of describing where this vector is pointing to. You know, for example, if it's there, we would call it positive with a length of 1. If it was straight in between, we would call that negative 45 degrees. And we would call it a length of 1 because it's on the unit circle. Okay, so keep that in mind. Now watch this. Focus here on the imaginary piece and the real piece. Again, those are the two pieces that tell you where this vector is. We would say the real piece is equal to the cosine of theta, where this is angle theta. And we would say the imaginary is equal to the sine of theta. For example, let's suppose theta is equal to 50 degrees. Could you calculate this triangle? Okay, we know it's going to be a right triangle. Because it's on the unit circle, we know this is going to be a length of 1 unit. Here's angle theta. If we go to our calculator and we type cosine of 50 degrees, by the way, be really careful with your calculator. Make sure that you have a D right here, that you're running in degrees. Okay, so the cosine of 50 is equal to 0.64. And the cosine of theta tells us the real part. So that's the part on this axis here. So that is 0.6428. Now we can do the same to determine the magnitude of this direction. So you would say sine of 50 degrees, and that is 0.766, which means my triangle is not quite proportionally correct. However, it's close enough for now. You could verify this very quickly using the Pythagorean theorem. That was a squared plus b squared is equal to c squared, where this is a, this is b, and this is c. So c is equal to the root of 0.6428 squared plus 0.766 squared. Let's try that real quick. So 0.6428 squared plus 0.766 squared equals, and now we want to take the square root of that. So square root of answer equals, and it better be 1. Okay, good. Okay, so c is equal to 1. Let's go back and look at that again. So given a triangle, given a unit circle and an angle, you could say that the real part, right, on the real axis is the cosine of theta, and the imaginary part is the sine of theta. Which relates back to our generator. We have a way of describing where the physical location of the coil is and what the actual output of our generator will be. So I used the word vector. A vector has magnitude and direction. So here is a vector. It has length. Okay, we would describe it as length, and it has an angle associated with it on the real and imaginary axis. We would describe this as polar notation. The other form is called rectangular. Again, same axis, the real and the imaginary, same vector, except this time we're going to talk about where we are. So we could say over r, right? So over so far on the real axis, and then up by some imaginary piece. Again, we would call that rectangular. Well, we're getting ahead of ourselves. I'll tell you what, we're going to come back to this another day. We're going to talk about the rectangular piece. We're going to talk about the polar piece. We're going to definitely use the word vector again. Again, a vector has magnitude and direction. Tell you what, let's finish the day with a quick discussion of trigonometry. You recall the sine of theta is equal to the opposite over the hypotenuse, where that is a right triangle, with this being the adjacent side, this being angle theta, this being the hypotenuse, and this being the opposite. Cosine theta, adjacent over hypotenuse, and tangent theta is equal to opposite over adjacent. And so those are 3 ways of describing a right triangle. Of course, you see where this is going. We're going to make a statement that this is the real axis, and we're going to make a statement that this is the imaginary axis. So when we were talking about these triangles, what we were really talking about is a vector. We're talking about a magnitude and a direction, where we have the real part and the imaginary part. Let's do one example and then we'll call it a day. Can you solve for the angle theta? On this triangle, we have the hypotenuse and we have the side that is adjacent to angle theta. So if we go back up here and we look for something that has the hypotenuse in the adjacent side, we find this. So we come down here, we would say the cosine of theta is equal to the adjacent over the hypotenuse, which gives us 140 over 200. We introduced this briefly in one of the previous videos when we talked about theta here and how hard it was to break out of jail. I used a silly story with the Sneetches, and I said that this is really easy. All you have to do is run it through the star off machine, and that is the inverse cosine machine. So inverse cosine of theta, and then what you do to one side you have to do to the other, of course. Inverse cosine of 14 over 20. That gives us theta on this side, and we can solve that using our calculator. So we go shift cosine. So we see that? Inverse cosine, so cosine -1 of 14 divided by 20. That gives us an angle theta of 45.6 degrees. Again, to break theta out of jail, we ran it through the star off machine, and what you do to one side of the equation, you can do to the other. So we ran both sides of the equation through the star off machine. That gave us a theta of 45.6 degrees. So 45.6 degrees. We could finish this off by solving for this piece. You could use Pythagorean theorem, or you could go back and use those trigonometry properties. I think we should use this one. So tangent of theta is opposite over adjacent. So tangent of theta is equal to opposite over adjacent. And now we'd say tangent of 45.6 degrees is the opposite. That's the one we're looking for over the adjacent. That's 140. We can use our calculator to solve for that opposite side as tangent 45.6 multiplied by 140 gives us 142. That makes sense. If this was a 45-degree angle, right, if this was 45 degrees, and we already knew that this piece was 140, we could say that this piece here is also 140. In this particular example, we are slightly greater than 45 degrees, so we would expect this one to be slightly larger. In this case, it's 142. I think this is a good place to stop today, so you can go back and work some of these trigonometry problems. Know that those triangles are going to describe vectors. Those vectors can be described in either polar or rectangular form. In both cases, we're talking about a magnitude, which is another way of saying a length, and a direction. When you come back, we'll talk about how these vectors can be used to describe the AC waveform that is derived from the generator. And I think you see some of it here, where we talk about the physical position of the generator, which is to say which angle it's at, and how that equates to a very particular voltage level. Until next time.